You should see the slides.
We do indeed. Thank you very much. Take it
Okay,
away.
thank you. Good morning, everyone. Sorry for the late start here. My name's Mike Waidson, and I'm an application engineer at Telestream. And in today's session, we'll be discussing some of the tools we can use to monitor and check on the various parameters of video, audio, and data programs. We'll be looking at the various ways to monitor these multiple programs with tools for shallow analysis to alert the user to issues. And then once we've determined a specific stream of interest, we can narrow our focus to the stream that comprise that program and look in more detail at what might be causing an error. So we have our typical broadcast network. It's necessary to monitor the ingest of the material. And we might have a sporting event or a live broadcast, which is coming into the facility. And we want to check for the presence of the video, audio, and data streams for the integrity of the signals. Then these signals are monitored at various points throughout the program of the network manipulation. So we might add some other additional graphics or content to the program, and it'll be manipulated as it makes its way through the broadcast facility to have some changes made to it. And again, when these changes are made, we might want to verify that those particular processes have actually occurred, that we've added the graphics, they're at the right level, audio is at the right level and it's present on the correct number of channels. All of these parameters, as we've manipulated the program throughout the facility, we need to be able to monitor and check that they're there and present. And then we'll finally distribute that program to the end customer. So at each of these points, we've been checking the video, audio, and data levels. For instance, the video and audio levels to make sure that they're the correct level for SDR or HDR content. And additionally, you might want to check the signals to comply to loudness for checking that they meet certain criteria for that program. And additionally, there might be the presence of metadata, such as closed captions or subtitles that are carried within the program. Now, these type of requirements for monitoring of the signal don't change from SDI to IP. Those remain the same, and we can monitor those without knowing whether it's SDI or IP. We're looking at the waveform levels. We're looking at the audio bars. We've got monitoring tools for measuring loudness or decoding closed caption. However, in the case of IP, how this video, audio, and data is carried and the new methodologies for monitoring and measuring these signals will change as we make this transition. We'll have to look for different parameters or different ways of monitoring within the IP stream. And we'll go through some of these approaches within this presentation. Let's start by looking at the process of converting the video signals to our packetized data for the video, audio, and data streams. This is going to take the stream of video, audio, data and packetize that with the addition of an IP header that provides addressing for the stream that's sent across the network. The real-time protocol header information used within SMPTE 2110 carries a sequence number that increments sequentially for each packet as it is produced from the device, along with a timestamp that's used to provide synchronization of the data at the receiver. The timestamp should ideally be generated relative to a PTP clock reference so that everything is synchronized within the output of the sender and should be then synchronized with the input to the receiver. So ideally, both of these devices should be locked to PTP that's going across the network. At the receiver, the device accumulates the packets into a buffer and reassembles the data based on that sequence number of that packet by packet. Hopefully, if there's been an out of order packet, we can correct that within inside the buffer by readjusting and shuffling the data around so that we can then have a sequential packet by packet structure when we start to decode the video, audio, and data. In some cases, we may not be able to do that in the buffer, and we might have to discard the packet, or the packet may not actually reach its intended destination. So we would need to make sure that those particular pieces are set up and monitored correctly in our network so that we can assemble the data back to the video, audio, and data streams that are necessary to produce our program. So what possibly, well, hopefully nothing in a well-designed and robust IP system. However, there are potentials within this system where we could have an error develop or possibly occur within a particular video, audio, or data stream. So it's important that we have correct operation between the senders and receivers within the system. And so what we'd want to do in these particular cases is we want to monitor those signals as they're routed between the senders and the receivers. And there are various parameters that we typically need to configure, such as the IP address or the multicast port, the payload type. And there's a potential that some of these values may be entered incorrectly and errors could be received and misconfigured with the stream. So it's important to be able to monitor those within the system. And these values may have been entered manually by an operator, or they may be automatically configured using an NMOS or orchestration server to configure these parameters from a session description protocol. Now that is a file that potentially is just a text file that could also have incorrect values within it. So there's a potential in certain cases with a lot of these different parameters for possibilities of error. And we want to try and warn the user of these types of error that may have occurred. The other part to mention is that timing and synchronization is critical within all these separate streams of video, audio, and data flowing through the network. And precision time protocol is key to ensuring senders and receivers are all locked to the same time. So we need to be able to monitor PTP throughout the network and ensure sources are locked. Unlike analog reference that is a one-way communication, PTP involves communication between the leader or the grandmaster clock and the following end device. Therefore, it's important that this forward and reverse path of communication is taking place for accurate synchronization of the devices. Network congestion and loading can cause packets to be laid across the network, which can cause jitter or even packet loss. And we need ways to determine what is happening in these cases and how to troubleshoot the problems within the network. To aid in the delivery of the packets from the sender to receiver, a redundant network can be set up that conforms to SMPTE 2022-7. Two networks carrying duplicate signal paths along path 1 and path 2 of the device. To these two separate networks, the network packets go through those two separate networks, and the receiver takes path 1 and path 2 and combines them back together. Now, the receiver can choose either path 1 or path 2 to assemble the packets, because it's going to do that on a packet by packet basis to assemble the video, audio, and data streams to ensure that they're error-free. To monitor these IP streams within a broadcast network, we're going to take several approaches to monitor and measure the various program content. Firstly, Telestream has developed Inspect 2110 that can monitor multiple programs within the network from ingest to distribution and provide operators with simple identification of problems by monitoring by exception. For instance, simple red-green indicators can help the operator to be alerted to problems by the various programs. So here we can see we've got two potential errors within these different programs over here that are shown in red. And we can then check whether this error is related to video, audio, or data within those programs. And this approach can help to identify the type of issue within the program and aid in troubleshooting the problem. For monitoring across the broadcast media network, Inspect 2110 provides two 100G data paths that provide wide bandwidth monitoring of the SMPTE 2022-7 redundant network, allowing the user to monitor multiple program streams of video, audio, and data simultaneously. Critical checks can then be performed on these programs for presence and correct operation of the streams within that program, monitoring the presence of PTP within the network to ensure that it's there and sending to each device. This simple approach simplifies identification of the problems that are easy to interpret by the user and allow identification of the initial issue quickly and easily. From the web browser application, once a problem has been identified, the user can investigate this issue further by viewing additional information on the stream that can make up this program. In this case, we can see that the two streams for path 1 and path 2 are not identically shown by the simple thumbnail images, and the operators and engineers need to be determined what is the cause of these problems or issues. It could be, in this case, someone has incorrectly applied the wrong multicast stream for one of the paths, or the input signal to one of the paths has become frozen, and so we'll need to further troubleshoot these issues in order to diagnose the device that's causing the problem. Also, within this system, we can look at a particular program and show the error log. For instance, the user might want to know how long an error has occurred for, or how many times a specific condition has occurred. The alarm log in Inspect 2110 can provide a detailed report. The log can be sorted by various criteria. For example, the user can sort the alarm log on a specific program. This can allow the user to see what type of errors have occurred within a program and provide trending information on the type of errors reported by the channel. Perhaps the errors occurred at specific times and is cyclic in nature, or perhaps a specific program has changed. These logs can be used by the engineer and team to investigate the issues within the program and provide important trending information. One of the many useful features within Inspect 2110 is the ability to compare the SDP file with the actual detected stream. The SDP file provides detailed information on the format and parameters of the stream that is typically used by the device to aid in decoding of the stream. It's a simple text file that should be formatted correctly and contain appropriate values for the stream. Sometimes this information sent within the session description protocol may have been entered incorrectly or assigned an incorrect value by an orchestration server or system. So it's useful for the user to be able to detect this because it could cause a potential issue for the device being able to decode the stream correctly. Within specific programs, the user can clearly see the difference between the detected signal format and the SDP file sent along with the stream for these set of parameters to be able to easily troubleshoot configuration issues in the system. For instance, we've detected a frame rate of 29.97, but the SDP file indicates that the frame rate is 23.98. And some devices may have a problem when decoding this stream because the information is incorrect. Inspect 2110 provides a wide ability to look across multiple programs at the same time to help identification of problems and possible causes of the issue. However, it provides a shallow analysis of the problem. And to further diagnose those issues, the Telestream PRISM can be used to troubleshoot them further. Additionally, by selecting the view in PRISM, Inspect 2110 sends an API call to the selected PRISM to automatically configure the instrument to the specific program that has the issue. So it will automatically configure the stream for the video, audio, and data, just like Inspect 21 is watching. This saved time for the user in both being able to diagnose the issue quickly while having the video, audio, and data streams set up within the same configuration between the two monitoring devices. In this specific case, Inspect 2110 has diagnosed that the two 22-7 streams are not identical, further aiding the user in troubleshooting this issue within the instrument. Now we can switch to a new tab that would have opened up to view in PRISM with another browser application, and the instrument is configured for the specific stream of interest. Now we can analyze the stream and determine what is the issue in the system. Since Inspect 2110 provided us with useful information that the two streams are not identical, this can narrow our focus to troubleshooting this specific issue. Initially, we'll look at each stream as a separate stream by disabling seamless switching in PRISM to help us identify the error that may be present within each stream. On analysis, the first stream shows no errors. The IP status shows us important syntax information for the data rate, the payload type, and the IP address, while the IP session shows a valid stream that is being decoded within the picture display. Since they're all green tick marks here, everything is good with this specific stream. We could also check in a similar way the secondary stream by configuring those parameters to see if any errors are present on that stream. And maybe in this case, the picture is frozen or not for that individual stream as well. We would also likely check the routing and configuration parameters to make sure that those are correct for the signals being applied and correct between the two paths in the network. And engineers can compare the information in the IP status with their expected values for the parameters from the device itself. We can also check the SDP file within PRISM within the NMOS tab of the IP session. So here you can see the checks on the particular parameters for this specific stream. You can see the display of the syntax of the SDP file and the specific information it contains related to the video in this case, or you can look at the audio or data streams. With a variety of parameters such as IP address, port number, RTP payload type, there's a potential for misconfiguration. And within a broadcast network, it can be useful to define some rules for specific parameters. For instance, the IP address values, or the port number value, or the payload type value. Typically, you can set these by the user, and these can be used to be aiding in identifying the type of stream. It'll make it much easier for diagnosing the issues within the system. For example, we can use the port number to help identify video, audio, or data by using values of 50,020 for -20 2110 streams, 50,030 for audio, and 50,040 for data. If you can see those parameters, then you know that this should be expected to be configured as a video, audio, or data stream. Alternatively, you can use the payload type. You have a range of values between 96 to 127, and so you could use type 96 for video, type 97 for audio, and type 100 for data. You can choose any of those values and choose your own specific one that suits your application. You could start at 100 and do 100, 101, 102, up to you. You can also use the specific values for the IP address to help identify the video, audio, or data packets. In the various AIMS interrupts, we used a combination of all three parameters for IP address, port number, and payload type to identify the streams and make sure all the various devices used had the appropriate addressing scheme. This allowed for a quick identification of problems. For instance, if you had a stream that was 10 megabits and it had a payload value of 96, well, that was an indication that you had video, but 10 megabits can't really be a video payload. And so this is likely an audio stream that's been misconfigured in this particular case. So those kind of strategies can help you identify the problems. The other critical part is synchronization of senders and receivers within the SMPTE 2110 network. And this is critical to ensure you have separate streams of video, audio, and data. And therefore, ensuring correct operation of precision time protocol is critical to ensure the devices are locked. To measure this within PRISM, you can use a number of displays, such as the timing display that compares the location of the incoming signal to PTP or the analog reference. In SMPTE 2110, only the image is sent, so the timing is offset by the vertical blanking. So you would expect a 1080i video to be around 21 lines for the vertical blanking, and 1080p video content to be around 42 lines for the vertical blanking. You will see an expected slight moving of the timing circle as it moves within this window, but it should not scroll line by line, as that would be an indication of drifting or unlocked reference from the sender. You can further graphically plot this information over time in the stream timing to monitor trending of that data over time. Now, stream time using PTP clock as a reference to which the device that's sending should be locked. The device will generate a 90 kilohertz clock for video and a 48 kilohertz clock for audio from the device internally. And then these will generate a timestamp value that is added to the real-time protocol header along with a sequence number and other parameters. Note that this timestamp value for all packets within the frame of the image will not change until the next frame occurs, at which time a new timestamp will be added. And the RTP marker bit should have a frequency of the field or frame, which is the indication for the change of that RTP timestamp. Therefore, it's also important to first check the PTP presence in the network and the syntax for domain, grandmaster ID, and PTP message rates. So typically, those would be 4 announce and 8 for sync delay request delay response, or there could be 1 announce and 8 for sync delay request delay response. And within the analysis, you can also look at the forward and reverse paths of the PTP messages, or use the phase lag to provide an overall trend of the PTP lock. And ideally, you'd want to see a straight line that would occur within the graphical plot to ensure that everything's locked. And you can look at this in a network over a period from 60 seconds to 1 day for trending of the network performance. So once you've identified errors within a program using Inspect, you can then analyze them within the stream of PRISM. And typically I go through a step-by-step process of checking the stream, firstly with the IP status, and then with the IP session to make sure the signals are being decoded and everything's got a green tick mark. If there's an error, then that'll be flagged as a red X. Then I'll check the PIT histogram to see what type of sender is being sent, whether it's a gapped or a linear. And if there's any network traffic issues, those might show as a spreading of the histogram packets as they're being received by the device. And then I'll check that the sender is locked to PTP for correct synchronization. And so I can monitor those particular pieces within my timing display to make sure the signal is locked to the PTP reference and it's not scrolling through. And I can look at the stream timing to see what the trending information is for the video to PTP offset, or I can actually regenerate the RTP timestamp based on the current PTP value and compare that, and that'll give me a network kind of value comparing what was being sent to what is being received. And if I need to troubleshoot the PTP issues, then I'll bring up the IP tab in IP session for PTP. I'll check the domain and the message rates, and then I'll check the PTP graphs. I'll also go into the IP status and look and see what streams are sending PTP messages, and I'll be able to check the PTP domain value, which is critical for all devices to be locked together. So that'll give you an indication that everything within those networks is synchronized. So the overall goal of monitoring the program is the same, to ensure the high quality of the video, audio, and data signals, and the methodology in analyzing the stream might be slightly different. You can use a combination of monitoring and measuring to aid in looking at your IP network. And for operators, there needs to be a simple task monitor for the multiple programs to ensure consistency and presence of the correct streams for each program. That you can monitor a wide variety of these programs simultaneously in an intuitive, easy to understand approach that can aid in alerting the user to an issue within a program or stream. And then you can do a deeper dive and analysis with automatically configuring the device to look at that stream of interest and analyzing the various tools that we've showed here to look and identify the problem and troubleshoot the issue. So that brings me to the end of this particular presentation.